Hey everybody, DeMoivre's theorem, a little exploration here. Getting fancy with derivation. So DeMoivre's theorem specifically works with this third equation here that I've got. But there also are a couple of applications here in red. Okay, and I'm going to derive those two in this video. I'm going to save the derivation of the last of the equations for a math induction proof. And I'll do that in a future lesson here in this complex numbers chapter. So I'm going to let z equal the complex number in modulus argument form, right? The modulus of z is r, and the argument of z is theta. And the complex number w have a modulus of t and an argument of phi. Okay? So if I drew z in the complex plane, generally speaking in quadrant 1, we got Cartesian form, where z is a plus bi. And we got modulus argument form, which would make this angle of rotation theta, and the modulus of z, modulus of z equal to r. So modulus argument form is polar in nature, so it's an extension and a rotation. So an extension of r and a rotation of theta. Likewise, w, again in quadrant 1, would look very similar, where w would have an angle of rotation of psi, and the modulus of w would equal t. No difference, just different values specifically, different assignment there. So we got our real portion of w, imaginary portion of w, and likewise over here for z. Okay, so let's jump into the derivation of these two red starred expressions. Okay, so I'm going to go ahead and scroll down here. And I'm going to do the multiplication first. Let's pick a color. How about yellow? That works for me. Okay, z times w. Well, we know that z is r cis theta, and we know w is t cis psi. Okay, so what I'm going to do is I'm going to do a quick rearrange here using the commutative property of multiplication. And I kind of lock in that r times t, which you can see above. What I'm going to do with the remainder is I'm going to expand cis theta, which is cosine theta, plus I sine theta, as well as expand cis psi, I don't know, whatever, which will be cosine phi plus I sine phi. Okay, now what I'm going to do, again, because I want to get this in cis form, is I'm going to group my real terms, which would be cosine of, oops, hold on, I messed something up here. Yep, definitely did. Got to multiply those. I knew that was a little too simple. Okay, so I'm going to do a quick double distribution, or FOIL, if you will. Okay, so we got some work to do. Let's dig into it. Okay, that'll be cosine theta, cosine phi. Okay, plus I cosine theta, this will be our outside, sine of phi, plus I cosine of phi, sine of theta, that's our inside, and our last will be I squared, which which is a -1, sine theta, sine phi. All right, now I'm going to group my real components, cosine theta, cosine phi. So I keep the RT. Cosine theta, cosine phi, minus sine theta, sine phi. That portion in red is equivalent to cosine of theta plus phi. Okay, go back to your trig identities for that one. Plus, I'm going to pull out an I. Right, I pull out that I there. That leaves me with cosine of theta sine phi plus cosine of phi sine theta. That's going to be equivalent to sine of theta plus phi. And you can see what's developing here. This portion is equivalent to cis theta plus phi. Of course, I tag the r times t in front, and there you have it. There's the derivation of an application of DeMoivre's theorem. Okay, cool. Now you can use that whenever you want to. When you multiply two numbers that are in modulus argument form, okay, two complex numbers, multiply their moduli together, add their angles together. Okay, that's your shortcut. All right, let's pick a different color. How about gray? Gray works for me. Let's work z over w. All right, so z was our cis theta. W was T cis phi. Okay, so I can see I'm going to have R over T. I lock that in place, right? See that right there. Now I'm going to do a quick expansion of cis theta. That's cosine theta plus I sine theta. In the denominator, I'll have cosine phi plus I sine phi. Okay, now I want to clean this up, right? I want to be able to combine this into one term, no denominator involved. So whenever you're trying to reduce the denominator of a complex number, you typically want to use the conjugate. So I'm going to multiply the denominator and the numerator by the conjugate of the denominator. Let's put that in green here. This will be cosine of phi minus I sine of phi. Okay, numerator, denominator, cosine phi minus I sine phi. Okay, now we've talked about this before. When I take z times z star, which is what I have in the denominator here, that is equivalent to the modulus of z squared. Okay, so I'm going to take cosine plus I sine. I'm going to call that z. Cosine phi plus I sine phi. We'll call that z. So I'm going to find the modulus of that. So I use the Pythagorean Theorem. So the modulus of z will equal the square root of cosine of phi squared plus sine of phi squared. Remember, you always just use the real component, imaginary component. You drop the I when finding the modulus. Okay, well, this is an identity. Cosine squared plus sine squared is 1. Okay, so if I were to square the modulus, it's kind of cool. I just get 1. All right, so let me find my gray pen again. So this will equal r over t. The denominator reduces out, right? That'll equal 1. So all I'm left with is cosine of theta plus I sine of theta times, I guess I should put that conjugate in green. And I just got to do a little work there algebraically. All right, let me make some space here. Oh, that's interesting. What's that doing there? Okay, I guess I'm stuck. All right, so let's clean that up. That'll be r over t. Okay, when I expand, I get cosine theta, cosine phi. Outside, I'll get negative cosine of theta. Oops, I'll put an I on there. Cosine of theta, sine of phi. Inside, I get a positive cosine, I cosine of phi, sine of theta. And last, I get a negative I squared, which is positive 1 sine of theta, sine of phi. Okay, so let's see what we get here. This is r over t, locked that in already. The real portion, cosine theta, cosine phi, sine theta, sine phi. All right, so by definition, and the trig that we know, all right, that will be cosine of theta minus phi. And the imaginary component will be, of course, I've got, let's pull out the I. Okay, that leaves us with, imaginary will go green, this here. Okay, this, by definition, since I have sine of theta, cosine of phi right there, and a negative sine of phi, cosine of theta, that is equivalent to sine of theta minus phi. Okay, so I can go one more step here. You might already see what I'm doing here. But z over w, when you divide two complex numbers, and they're in modulus argument form, you divide their moduli, and you subtract the angle from the numerator minus the angle in the denominator. There you have it. Very good. Short little video on deriving those two properties. Again, like I said, when we get to the math induction lesson, I'll be proving this portion of DeMoivre's theorem using our friend, math induction. All right, guys, we'll see you in the next video.